translation was sort of the hallucinogen of choice, but it can make you thinking fuzzy. There's a way to know when you've had too much, when you look at this molecule very carefully and it's all set up just right. It starts wagging its tail at you. And it's time to quit. Well, so, efficiency has to do with the energy being shared equally amongst all these various chemicals. And those are what they are. They're translation, rotation, vibration. So for simple case, monatomic gas, it has only a translation. Normally, we have energy of a molecule. Here's the energy of translation plus energy of rotation plus energy of vibration. And the monatomic molecule just has only this. So the energy of translation is equal to E x direction, translation in x direction, and they're right down, plus energy translation in the y direction, plus energy translation in the z direction. And the average energy, we just said, was 3 halves kT, and I drew a box around that because I want you to remember that. Therefore, the average energy of translation is equal to 1/2 kT per degree of freedom. So that's the conclusion we come to invoking the condition on translation modes of Markov molecule. So the total energy of the molecule, total energy of a mole of molecules is equal to the number of molecules in the mole times the average translation energy, and that's the number of molecules in the mole, and the average translation energy is 3 halves kT. So that's the number of molecules in the mole times K times 3 halves T, and we've talked about that several times today. What is that number? What's the name of that? Thank you. You got to quick it up about this stuff. So it's 3 halves RT. Now, suppose just make it up. But suppose we have a gas in some volume at some temperature and pressure. So monatomic gas. So we take the gas at T1, both gas at T2 and T2, and specify that the volume is fixed, constant. So we have to put some energy into this. We define the heat capacity at constant volume. That's where you heated that gas at constant volume. Is equal to the derivative of the energy, that's how much energy flows through it, divided by the temperature change, constant volume, or it's delta T, delta T, the constant volume. So that's a measurable thing. A monatomic gas theory tells us that the heat capacity at constant volume on a molar basis is the derivative of 3 as RT spec T constant volume. And what is that derivative? Somebody tell me. Hmm? I can't hear you. Yeah, we have some. Okay. Oh. Atomic acid. That's a prediction that the theory makes. So here's a case where you go from the interpretive theory and you move up to the observational part of the triad and say, check this out. Measure. So what do you have to do this to make that test microscope? You have to have a monatomic gas. Well, it wasn't until late in the 19th century and early 20th century that the monatomic gases were discovered. So nobody could do this experiment, even though the theory was there and what you should find. But when those gases were discovered, every one of them was stable. Helium, neon, argon, krypton, xenon. Every one of them had the same heat capacity. This is joules per K per mole. And that turns out to be 3 halves R. So something else explained by the kinetic. Now we get to the real heat of the implication stuff that you really have trouble figuring out. So number 7, heat package of metals. You said, well, hell, we have only a theory of gas. But wouldn't it be wonderful if they could explain some behavior? Solids and liquids? Wouldn't it be fabulous? Ooh, that'd be up on a much higher mountain. Got up there and said, damn, this theory tells us something about the behavior of metals. That's what we're looking for. All right. So, in 1819, Dulong and Petit, by that time, people, the list of the periodic law hadn't been discovered, but the list of known elements from which one was able to make that organization and live, Mayer were able to figure that out. Those elements had to be discovered. Never been discovered at this time. And this, as they come along, you want to do what? You say, well, what's the behavior of metals? So you find a new metal, you try to find out all its properties. Good. Chemical properties, physical properties. Heat capacity is one thing to measure. That just on the per unit mass, like gravity, heat capacity, gravity, called specific heat. And those things are measured. So here are some metals that were known by this time, and the specific heats on a gram basis. And but Dulong and Petit said, well, now we also know about atomic weights. They were being discovered and written down by guys like Dalton and Muriel. So they multiplied each of these by the atomic mass and got the heat capacity on a motor basis, and just call them out here, and they look at that and say, "What the hell?" You know, within our strip of uncertainty, those all the same. Around 6 calories per mole per degree. And they scratch their heads and say, "Oh, why?" And if I said, "Beats hell out of me, I don't know why." But we may not have discovered the law of nature, but we've at least discovered a rule of thumb. And so there is the rule of the law to keep. Which is that the heat capacity I'm not going to put a V or a P on here because that was going to change volume much when you warm it up and it takes a little bit. It's equal to the specific heat. I don't have a notation of that times the molar mass. And that is of the order of magnitude of 6. I've written calories, but that's how they were taking data in those days. 6 calories per degree centigrade. That's the temperature scale they were using. It's the same as the Kelvin in terms of size per mole. Celebrated rule of long heat. Now, here are the questions. Naval theory supports the view that gases are made of molecules. It's not a big stretch of imagination because gases contain one of the common aggregates of matter, gas, solid, liquid, and matter can undergo changes between these states. If gases are made of atoms, that's not unreasonable to assume that other. Could make that. All gas molecules have energy in accordance with the temperature. That's a postulate. You see that there's some basis for thinking that's reasonable. If a molecule gas confined inside a metal container in equilibrium, the atoms of the metal walls must be coming in thermal equilibrium with gas molecules. They have to share energy. Equilibrium maintained by collisions of 3 molecules with the locally constrained atoms of the metal. Now, crystals, including metallic crystals, have regular geometric shapes, which suggests that the atoms of crystals are arranged in 3-dimensional geometric arrays. I know you know all this stuff. That's something I had to sit down and go through this reading. So we postulate that each atom in a metal crystal is tethered to its specific lattice side by some kind of restoring forces, which at that time were unknown. We postulate they're there. If the atoms of the model metal were all at rest, they'd just be sitting there at their lattice sides. But when not at rest, when they being beat around by rattling against one another and being banged by gas molecules from the outside, when they're not at rest, then they're oscillating around their lattice sides. 3 dimensions. 3-dimensional. Based on these ideas, we can extend the KMP to include condensed states of matter, especially metals. The simplest model we can create consistent with these ideas assume that metal is a collection of 3-dimensional oscillators tethered to lattice sides by restoring forces proportional to displacements from the reservoir. And I say a simplified atom of such model is illustrated below. Here's below. So there's an atom in the metallic crystal. And it's sitting there, and I don't mean they're springs, I just mean that they're forces. I represented 3 sets of them because it's 3-dimensional. When it moves away from the equilibrium side, there was a storing force pushes back. And it comes back, it overshoots, and then oscillates. Don't you see how the heat fission theory was sort of saying that's when you have a turn of this and see what we can say about it? Yeah, I think it is. don't have a good model of a three-dimensional oscillator. I got a Kruger that I made of a two-dimensional oscillator. So, I got a ball bearing. I just stuck down in this spring. Can you see that sucker wobbling around in two dimensions? As soon as the magnet's doing something up and down at the same time, you got an idea. Pretty crazy what goes on down these nuts. So our model is that a metal is a collection of three-dimensional oscillators. So each atom has three vibration degrees of freedom, and if it shared for the potential, the partition of energy by the impartition theorem, then when something's vibrating, it has kinetic energy because it's moving, but it has, there's something, I can't make that thing vibrate very easy, but I can make that. Okay. So what's happening? Kinetic energy, but it stops, no kinetic energy, it's all potential. It stops, all potential. So there's a trade-off, constant trade-off, kinetic potential, so oscillates. In the paper, the lecture that I will post, there's a nice graph of that and a calculation of this. The energy is with the one dimensional oscillator because just each atom has 3 degrees, 3 single degrees of freedom. So just looking at one of them, we have the vibration, say in the X direction, is equal to kinetic energy in the X direction plus potential energy in the X direction. And the restoring force to the displacement. This is Hooke's law. I know all you engineers know this well, and the chemists supposed to know too. But force is always the negative gradient of a potential. So we have minus KHK is equal to minus the gradient. That's a change in the potential energy with respect to X. And you can integrate this from 0 to EP from 0 to X. And you can find that the potential energy is 1/2 KHX squared, whereas the kinetic energy is always 1/2 mVx squared. That's the X direction. X direction. Ah. Yes, I know, but I'll get to the other day. All right. So it always happens like this. You get right to the stopping point. Okay. So each oscillator, Higgs efficient says you get 1/2 kT there on average, and you get 1/2 kT there on average. So that the energy of vibration for metal according to that theory is equal to Avogadro's number times 1/2 kT plus 1/2 kT is kT per vibration mode times 3 modes per molecule. So it is 3 nKT. So that's 3 RT. The heat capacity turns out to be, and shut up. 3R turns out to be 5.96 calories per Celsius per mole, and that's about 6, and that's the rule of thermometer speed.
Thank you.
Alright. Now that, my friends, takes us to a nice mountain top, a good place to leave here. If you use fuzzy because it's cloudy, then just read this paper this afternoon to clarify it and enjoy it. Alright?
What are you guys?
And the last one,
Yeah.
calorie or is
Per degree Celsius mole.
yeah.
Where was it y'all?
Kimmy's student center.